Hello everyone, and welcome to today's webinar, Build a Secure Cloud with AWS and HashiCorp Vault. Please feel free to type your questions during the webinar. We compile all questions and answers at the end of the webinar and send the results to everyone registered. This webinar is recorded, and the recording will be made available after post-processing, usually within about 2 days. With that, let's go ahead and get started.
Hi everyone. I'd like to also add my own additional welcome. My name is Seth Vargo, and I'm the Director of Technical Advocacy here at HashiCorp. So today we're talking about Vault, and for those of you that aren't familiar, Vault is a tool for modern secrets management. And at HashiCorp, we make tools that enable developers to provision, secure, run, and connect any infrastructure to any application, modern, legacy, whatever. But in order for us to talk about what we mean by modern security, it's important to take a step back and talk about what we mean by not modern security. Specifically, what changes introduced new challenges to modern application development, and then we'll talk about how Vault tries to solve those. So let's take a journey into the past, maybe 10 or 15 years ago, and talk about a traditional monolithic architecture. Your traditional monolithic application had a customer-facing load balancer, something like an F5, in a physical data center. You had a firewall that did TLS termination, and then you had a big monolithic application, and all process handled inside of the application. So there was no multi-process communication. The database, everything was on the same physical server. You had physical control over that data center. And again, there's no external processes or communication. In this architecture, the biggest security risks are physical machine access, someone actually breaking into the data center, bad code, code exploits, kernel exploits, and humans making physical mistakes. Now, when we compare that to like a modern architecture, like a service-oriented architecture, we still have that load balancer, but that load balancer lives on some type of shared infrastructure. That might be a cloud environment, such as like Amazon or Google, but it might also be your internal virtual machine farm running something like VMware or ESXi. But the resources are shared. You're competing for compute and memory among other applications and other services that are running in that data center. Instead of a physical firewall appliance, we have security rules or firewall rules that again might be running at a software layer instead of a hardware layer. And instead of a monolithic application, we have these independent services that do one thing very well, but they're not all together. We have to network them. We have to communicate using something like API calls or RPC calls between these services. And furthermore, each of those services is capable of their own scaling. We might run multiple copies of one instance because it requires additional work as opposed to another instance. Messages flow between these services, and sometimes in modern applications, we might even be communicating with APIs or services that live outside of our data center. A good example there is something like Amazon's hosted database service, Amazon RDS. The biggest security threats in these environments are actually unauthorized access, unauthenticated API endpoints, long-lasting and unrotated credentials, and lack of a break glass procedure. And what do we mean by break glass procedure? Well, as you start adopting better security practices, what any security professional will tell you is that at some point it becomes less about how secure you are after you've dotted all your T's and crossed all your I's, but it's more about how quickly you can react to a security intrusion. So it becomes about detection and response to that detection. So tools like anomaly detection software and being able to quickly revoke or rotate credentials to limit the scope of a security breach becomes as equally important as preventing the breach in the first place. Additionally, because we have all of these services that are running, how do we know that that service is actually authenticated and authorized to retrieve data from the database or communicate with another service? We have to implement things like message signing, because if an attacker is able to launch an instance inside of our private VPC or private network, do we just inherently trust everything running on that network? And in a monolithic application, that used to be the case. But now that we're running on shared infrastructure, we can't trust anything. We don't trust our cloud provider. We don't trust our application code. We don't trust individual applications. And this is really the reason that we built Vault. So Vault is a free and open source tool that's a member of the HashiCorp product suite. If you're not familiar with HashiCorp, you might recognize some of these logos here. Vagrant was our first open source tool. It's a tool for building automated development environments. Packer, which is a tool for automated machine images. Surf and Console, which help us the gossip layer and service discovery distributed key value store. Terraform, which is a tool for managing infrastructure as code. And Nomad, which is our application scheduler. But today, we're obviously focusing on Vault. If you have any questions about the HashiCorp tools, please feel free to leave one in the question section, and we will answer it as soon as possible. So what is Vault? And I know that there are some people on the line who might be listening who are familiar with Vault, so this might be a little bit boring, but we have some people who have never heard of it before. So in its simplest form, Vault is an encrypted key value store. The simplest way to think about this is encrypted Redis or encrypted memcache. Data is encrypted in transit and at rest, and policies and ACLs guard access to that information. So just like you can put some data in Redis, you can put some data in Vault. The difference is that when you put that data in Vault, it's encrypted both in transit and at rest. So even if an attacker is able to gain access to Vault's data, they would have to brute force that decryption. And if they're sitting on the same network, we use TLS to encrypt the transmission of that data. But we push the bar even further, and Vault can actually act as a pass-through encryption. So instead of storing those encrypted values in Vault, which cause Vault's database to be large, we can actually return the encrypted data to you, providing encryption as a service or secrets as a service. This is really great for applications that store data that are backed by something like a database, like a web application. The web application receives some customer data, something sensitive like a credit card number or a social security number that we can't just hash. We have to be able to decrypt that data. Instead of having the application build, a AES 256 CBC encryption and do all of the math and academic research and build an asymmetric encryption algorithm, you can use Vault's encryption as a service. The application just makes an API call to Vault with the plain text. Vault encrypts it and gives the application back the encrypted text. The application then stores that encrypted text the same way it would store anything in the database. And when it needs the plain text value, it communicates back to Vault and gets the plain text value back. This is beneficial because the application doesn't even know the encryption key. So even if an attacker is able to compromise the application and download the encrypted data, they would have to also compromise a Vault in order to decrypt that data. And this entire process is not only authenticated, but audited. Every request and response is audited, with secret information being HMAC'd in those audit logs. Again, these two features don't really separate Vault from other tools that exist on the market. Where Vault does do its separation from other tools is that its ability to do dynamic secret backends. So Vault can do more than just act as a security store. It can actually generate credentials on the fly. After configured, Vault can connect to a database like a Postgres database or a MySQL database and run all of the necessary commands to generate a login for that credential, a username and a password, and then return that credential to the requester. Again, this whole process is completely audited and authenticated. Unlike a traditional credential, I know a lot of people here might not be familiar with databases, but usually you run some type of SQL command or some type of terminal command to generate a user, and that user basically lives forever until someone goes in and manually rotates it. Unlike a traditional credential, Vault-created credentials have a lifetime or a lease. So very similar to something like DHCP or DNS, where you get an IP address or a DNS name and it has a TTL or a lease associated with it. Those credentials expire over time. So what this means is that if Vault generates a database credential, we can guarantee that that database credential will be valid for at most 30 days or any configurable amount of time. Not only does this help with compliance, because you can tell a compliance officer, yes, we guarantee that all credentials are rotated in this period of time, but when I explain more about Vault's leasing model, you'll see that it significantly reduces the surface area for an attack. Instead of sharing the same database credential across all your application instances, each application has its own username and its own password to connect to the database. If one application instance is compromised, you can revoke that one credential, and all the other applications continue to function as expected. This can help reduce or eliminate downtime in the event of a security breach, all the while each request is audited and authenticated, so it's possible to trace things easily through the system. And we can continue extending Vault's dynamic secret backends to do really amazing things. So Vault can generate secrets from more than just databases. Vault can actually connect to AWS and generate IAM users that are attached to predefined policies. Just like database credentials, these IAM users are revoked after the lease expires. But you don't have to log into the AWS console or run any AWS CLI commands to do this. It's just one HTTP API call with all the authentication and authorization and auditing, and you get back an IAM user. That IAM user could be valid for a year or 5 minutes. All that's configurable. And again, we continue to push the boundaries of what Vault can do. Vault can manage your entire PKI infrastructure to ensure secure, mutual TLS authentication between all services in your network. I don't know about you, but I never remember the magical incantation of OpenSSL commands to run to generate a self-signed certificate or sign a certificate with a CA. I always end up copying something from Stack Overflow. With Vault, that goes away. You can actually say goodbye to these long-lived certificates and painful OpenSSL commands because Vault can easily generate certificates that are valid for only a few hours or minutes, and it's just an API call. You don't have to remember all of those crazy flags to pass to OpenSSL. And we can push that even further. One of the new features in Vault 0.7.2 is Vault's ability to sign SSH keys to establish remote connections via the SSH protocol. For those of you that might be familiar with like a Puppet, Chef, Ansible, or Salt background, you'll know one of the early exercises in config management is writing out an SSH authorized keys files on staging or production infrastructure so operations engineers and developers can acquire production access to servers or machines in the event of a debugging situation. This is challenging because as new people join the company and leave the company, you have to manage that file over time. And it's very easy to forget to remove someone. With Vault's SSH CA backend, Vault actually signs your local SSH key, the same one that you're using to connect to production infrastructure. We don't write that to an authorized keys file. Instead, we delegate to Vault. So when you try to SSH into a machine using the same SSH credential you would use to push code to GitHub or SSH into your blog, we first check if that key has been signed by Vault, and if it has, you get the proper access as dictated in the policy. If not, you don't have access to the system. But unlike an authorized keys file, this is a time-based access. So you may have access for 5 minutes, or you may have access for 10 years. Again, all of this is configurable, and it gives operators and security professionals a lot of flexibility for how people are going to interact with these production systems. In an ideal world, no developer or operations engineer would ever SSH into production. But we know there are those edge cases, debugging things at 2 in the morning. Sometimes it's the best solution that exists at the time. So there's no need to use configuration management to write out an authorized keys file anymore. And there's no need to create custom keys or manage keys. Just use the same key you're already using and ask Vault to sign it to give you SSH access to machines that are managed by Vault. And more recently, we're kind of pushing the boundaries of what we consider a secret to be. Vault can generate TOTP codes. TOTP or OTP is like those 6-digit codes that you get for 2FA or MFA, two-factor auth or multi-factor authentication. While Vault doesn't provide the same pretty interface that something like Google Authenticator or LastPass or 1Password would provide, this is really great for providing shared TOTP codes for infrastructure or code, such as, I don't know, perhaps enabling multi-factor authentication on your AWS root account. Obviously, no one should be logging in with the root account except in certain situations, but it would be nice to have multi-factor authentication in that. We can configure Vault to be the authentication app for that, and then using authentication and authorization, only certain people would be able to access the two-factor authentication code. Again, it's just an API call away. And then one of my favorite new features in Vault is that Vault can actually be on the receiving end of TOTP codes. I have personally built a multi-factor authentication system before in Rails, and it was probably one of the most painful things I've ever done as an engineer. I don't know how many people on the call have ever built a two-factor authentication system by following the RFCs and the specs, but it's really challenging to get correct. In Vault, we've built two-factor authentication as a service. So you can easily enable two-factor authentication in your client-facing app with just a few API calls. You delegate all of the responsibility, both the token generation and authentication, to Vault, and your application doesn't have to know anything about ToTP, but you still get all the benefits of the security that it brings. So that's just a very brief overview of some of the features of Vault. Vault's surface area is very large and it's continuing to expand. And to show you that, I'd like to do a quick demo. So I'm going to jump over here. All right. So here I have a Vault server that I've set up in advance. And this is just a standard Vault 0.7.2, but I'm running the enterprise build, so there's a UI available. I can go ahead and run the Vault status command, and this will show me that this Vault is up and running. I'm running it in development mode. This information isn't super important for this demo, but it just showed you that the Vault is up and running. I said a few times that everything is authenticated and authorized. So in order to communicate with Vault, I need to authenticate to Vault. I've gone ahead and created a user in advance. Root is the username. So I'm just going to go ahead and log in as that root user. It's important to note that what I'm doing here isn't necessarily considered Vault best practices. This is optimized for a demo, not necessarily 100% security. Usually your authentication is a really long UUID, but I didn't feel like typing that. So I just used some of Vault's internals to change that to ROOT. Again, kind of following the same pattern that I used in the slides, the first thing that Vault is basically an encrypted Redis or an encrypted memcache. So let's see what that looks like. So I can write to secret foo with a value of bar, and you'll notice right away that this doesn't exactly feel secret. And I can read that data back out. So I can read secret foo, and I get back that data as well. And this might not feel secret, and that's because as an industry, we've almost been conditioned to believe that security has to be hard. We match difficulty with security, and it doesn't have to be that way. Vault has been audited a number of times independently by the NCC group, and it continually passes with flying colors. So we know the data that we're doing and the operations that we're doing are secure, but it might not feel secure. And again, that's because as an industry, we've been a little bit misconditioned. I can update values, so I can update that new value to banana if I'd like. Spelled incorrectly, and I can read that data back out, and you'll see that the value has been updated. It's also possible to list the particular data, and we can delete data as well. So your basic create, read, update, delete, list operations, the same type of things you would get, again, with like Redis or Memcache. This data is encrypted in transit and at rest. So if an attacker was on this particular system, they would not be able to compromise this data. So let's talk about semi-static secrets, and that's that transit backend, or the encryption as a service. So I'm going to go ahead and enable the transit backend. And the way the transit backend works is I first create an encryption key. Now, I don't have to run a bunch of OpenSSL commands to generate that key. I just have to give Vault a name. And this is, you can think of this as like a symlink or a pointer to the key. So I'm going to give it a human-friendly name, which is called, my key, or maybe it would be like my application. And Vault under the hood will generate a high entropy, secure, asymmetric encryption key. Now, anytime I want to encrypt data, I need to tell Vault that I want to use my key. And to decrypt data, I have to use that same my key. So this is a human-friendly label, if you will, that corresponds to an encryption key. Under the hood, it's actually a key ring, so Vault can support rotation, auto-upgrading, and changing that key ring under the hood. So you can easily rotate these and do auto-upgrades on the fly, but I'm not going to cover that here today. So what I'm going to do is I'm just going to encrypt some data. So I'm going to write to transit encrypt my key, so I'm saying encrypt the data at my key, and the plain text that I'm going to give is going to be foo. Now, because there's no guarantee that the data that I'm giving to Vault is actually representable as text, I actually have to base 64 that data. So I'm just going to go ahead and base 64 encode foo. And notice that we'll get back ciphertext. And in this case, the ciphertext is prefixed with Vault and then the key index, in this case v1, and a bunch of base 64 encoded ciphertext. This value here is what I would put in my database, put it in Postgres or MySQL or MongoDB and forget about it. But now I need that plain text back. I need to do some type of operation, maybe batch processing or run a credit card. So in my database, I'll pull this data back out. So I'm just going to copy this to my clipboard here. And to decrypt that, I make a call to Vault. So transit decrypt again, the same name of the key, and I pass in the ciphertext. So I'll just paste that in. And you'll notice that I get back this plain text value here. This plain text value is base64 encoded, again, for safe transport, because we could be encrypting, a PDF or an image here, or just any binary. So I'm going to go ahead and run base64 decode this value, and you'll notice that I get back foo. So this is basically pass-through encryption, or encryption as a service. The transit endpoint also supports derived keys, which enable a piece of data to be encrypted with a unique context. So each request I make generates a new encryption key, so that if an attacker was able to brute force your database and get the first encryption key, that encryption key would not actually decrypt the second row of data or the third row of data. It's important to note that all of the commands I'm running here are actually API calls under the hood. Vault's CLI, the VAULT CLI, is nothing but an API wrapper and text formatter. So the API is a JSON API, and all of the commands I'm running here can be replicated easily via something like curl or HTTP. So if you're working in a programming language that can make HTTP requests, you can interact with Vault. You don't have to have the Vault CLI installed or anything. So let's take a look at dynamic secrets now. Go ahead and clear this screen. I'm going to mount the new unified database backend. In order for Vault to generate users, we have to tell Vault how to connect to the database and how to create the users. So because I suck at typing, I've gone ahead and created this little connection string in advance. So I'm telling Vault to connect to a local Postgres database on the database named MyApp. So we'll go ahead and run that. And now we have to tell Vault what SQL to run to create our user. Vault doesn't know which tables we want to grant access to. Should it be read-only, read-write, delete-only, update-only? Those are things that, as a user, you have to decide. And we do that by providing you the ability to create what are called roles. So here I'm creating a role that is named read-only that, as its name implies, creates a read-only role on this particular database. So it's going to run this SQL. The things in the curly braces here, name, password, and expiration, get filled in by Vault dynamically each time we run this. So let me go ahead and run this. Now I have a role named read-only. Now when I read from database creds read-only, Vault actually goes, establishes a connection to the Postgres database, runs that SQL filling in the things in those curly braces, creates the user, and returns the username and password to me. So this is a real Postgres username. This is a real Postgres password that could be used to connect to this database. Let me show you that. So this is the Postgres console. And you can see here that there is, in fact, a user that matches that username that was existed in Postgres. And you'll notice that that password is valid until June 1st, I don't know, that's UTC time. 2017. Vault uses the backend's expiration when possible. This means that even if an attacker was able to launch like a denial of service attack on Vault, Postgres would still revoke this credential. So it has a lifetime, and at the end of that lifetime, the secret's automatically revoked. Notice that each time we run this, we get back a different username and password. So each time we read from this endpoint, each time we hit this endpoint, Vault makes that connection to Postgres and generates a new user. Here I'm on one instance, but you can imagine each application making a request to Vault to get its username and password at boot time, and then it has its own username and password to connect to the database, with the permissions that your DBAs, your security team, granted. Let's take a look at a similar situation using the AWS IAM Backend. So again, I have my connection. And all I'm doing is I'm giving Vault my privileged connection, my privileged credentials. Vault will use those credentials to create other users. So we'll go ahead and run setup AWS connection. And then I have an IAM policy here. This IAM policy just grants all IAM permission. So any user I create that's attached to this policy will have the ability to do anything on IAM resources, but not EC2 or ECS resources. So just like we made a read-only role before, we have to make a role on the AWS backend. So I will write to AWS roles, and I'll call this one dev. And I'm going to attach that IAM policy. The @ sign just says read from disk. So what this does is that reads that from disk, uploads that policy to Vault, and creates a role named dev. So now when I read from AWS creds dev, so we create a role, we generate credentials, this is actually going to make an API call out to Amazon using the credentials that I configured and generate an access key, a secret key, and an optional security token. Now, this is a real access key and a real secret key that we made to Amazon, and it's valid for 768 hours. Again, notice that each time we run this, we get a new access key and secret key. And if I were to log into the AWS console right now, you would see that these users exist. 768 hours is a really long time, though. I think 30 seconds or maybe 5 minutes is a better option. So let's change that. The lease equals 30 seconds. The maximum lease is 5 minutes. What this tells Vault is now when you generate users, make them only valid for 30 seconds. Now, unfortunately, this doesn't retroactively apply. And you all have seen a number of credentials that are actually tied to a real AWS account. Oh no, this is a real webinar. How are we going to fix this? Those credentials are valid for 30 days. Well, thankfully, Vault has built-in break glass procedures. So we can easily revoke any one of those secrets, or in this case, because I'm not sure the surface area, I'm just going to go ahead and revoke all of the AWS credentials. What Vault just did is it made a connection to Amazon using the Amazon API, and it went through and it revoked all of the AWS users that it created. It didn't touch any of my other AWS IAM users, but it deleted the ones that it created. So just like that, we've completely mitigated the attack surface. And if any of you happen to grab a screenshot and tried to talk to the Amazon API with those credentials, you would be unable to do so at this point. So it's that easy to recover from something like an accidental security leak on a webinar, for example. The last thing I want to show you is the ToTP generator, because I think it's a really cool demo. So I'm going to mount this ToTP backend, and then I have generated a OTP URL in advance. So this is, I think this was from Dropbox or something like that. I'm just going to copy this URL, and now what I'm going to do is I'm going to write that to a key. So this is effectively the same as scanning that barcode that you get whenever you use something like Google Authenticator or 1Password. You scan that barcode with your phone. That's actually what's encoded in that barcode as a URL like this. So we've given that data to Vault, and now when we read from TOTP code demo, we'll get back that 6-digit code. And this is the same 6-digit code that you would get if you were using, again, something like Duo or Google Authenticator. And the timing worked out. Oh, the timing worked out perfect. So you'll see that the code changed because we hit that 30-second rotation period. But as I said before, Vault can actually act as a ToTP provider. So we can write to ToTP keys my app. So just like before, we will say to generate. So we'll enable generation. We will say that the issuer is Vault demo, and the account name is going to be Seth@HashiCorp.com. And notice I got back a whole blob of text here. There's 2 items here, a barcode and the URL down here. So what I'm going to do is I'm going to first copy this URL to my clipboard. And I'm going to jump over to 1Password. And I'm just going to make a new login in here. So we'll call this Vault demo. And in this section down here, I'll generate an OTP code. Oops. Math is hard. And I will just paste that URL in here. And when I click Save, we'll actually have a 6-digit code that rotates over time, and we can verify that against Vault. And that'll expire. And Vault authenticates that. But Vault also generates a barcode. So if you're looking for a better user experience, we can actually, you'll get this back via the API. It's a base64 encoded PNG. So I'm going to go ahead and jump down here on my local laptop, and I'm just going to run base64 decode on this data that's in my clipboard and pipe it to a PNG. So I'll just paste that in there. And now when I open that QR code, which is over here, that's a real QR code. I can jump over to 1Password, and instead of copying and pasting that URL around, we can make this a bit smaller. We can click Edit, and bring the little security scanner over that you're very commonly used to, click save, and we get the same 6-digit code. So you can provide that same workflow that users are used to, but notice that I didn't write any TOTP code. I made, I think, 3 API calls, and it just works. So we can then take this code that I just got, and we can try to verify it by passing in the code, and it's currently valid. And if we wait a drift period, it'll be invalid, just like typical TOTP. So that concludes the demo. There is a Vault Enterprise instance that's running. So Vault Enterprise includes a UI. If you go to vault.hashicorp.rocks in a web browser and log in with the token root, ROOT, you'll be able to see this enterprise binary. It includes not only a UI for interacting with a bunch of data in the system. Here's the generic secret backend. I can create a new secret. So instead of using the CLI, we do have a UI for this, but it also has more information about the policies and a lot of cluster management built in here. So that concludes my section here. I'm going to hand it back over to David to talk a little bit more about how AWS and Vault works together.
Great, thanks for that, Seth. I'm going to fire up my screen here, and we can see my slides. All right, great. So that's a very cool demo. It's not the first time I've seen it, and it's definitely cool stuff. So I appreciate all the work you did on that, Seth. And welcome. I'm David Potes. I want to talk a little bit about AWS security and kind of how we look at and approach security at AWS. So at AWS, security really is job zero. I mean, we actually say this all the time, and we kind of back it up with processes and people and tools. And there's a familiar security model. So if you're familiar with kind of how to stack these things together, this is going to look really familiar to you. And we're really validated and driven by the security experts at our customers. And all of our customers get the benefits of this robust security infrastructure, whether you're large or small. And it really is our top priority. And when we talk about security at AWS, we talk about the shared security model and how we share responsibility with you, the customer, in our approach to security. So we're responsible for the security of the cloud. So physical locations, database, networking, storage, underlying compute. And then what you really get to do as the customer is that you get to define the controls in the cloud. So you get to define where you can do encryption. The short answer is everywhere, because you can. You manage the inventory and configuration of your systems. You're responsible for network security using the tools that we give you, and also identity and access control. And I'm going to dive into that in a little bit in talking about our IAM service. But first, I'd be remiss if I didn't share some of the logos of organizations that have validated and certified our controls. So everything from MPAA to various governments to CGIS, FIPS. I think you'll see some logos you recognize here. And what this means is that you benefit from this environment that's built for the most security sensitive organizations, companies like banks, NTT Docomo, the NASDAQ market, government agencies, and we manage over 1,800 of those security controls, everything from who can get into buildings to segregation of duties and all of the things in between. And based on the sensitivity of your workload, that gives you the opportunity to kind of dial in the controls as you see fit for your workload, your business, and your requirements. And you always have full ownership and control of your data. So that's yours. We don't have access to it. Now I want to dive in a little bit and talk about the IAM service, and that stands for Identity and Access Management. And really, sometimes this is called AAA. What this is it gives you really fine-grained control over your AWS cloud. There's features that allow multi-factor authentication, which I always recommend. And you can even integrate an existing Active Directory using Federation and single sign-on. So I want you to walk away with some best practices here around IAM. So all apologies to David Letterman, but here's our top 10 best practices. So create individual users. We don't want to use shared accounts because we're looking to audit and track, what people are doing. And not just people, but applications as well. And we want to be able to do that through the use of individual users. Configure a strong password policy. Don't cheat on this. This is something that's really critical. You don't want somebody banging away, and brute forcing something. And you don't really want it something that can be easily shared. And using tools like Vault makes it a lot easier to manage those. Rotate your security credentials regularly. The sad truth of it is that it is possible for things to leak, and if you're rotating credentials regularly, you really reduce that blast radius should you have a security incident in your application. Enable MFA, so multi-factor authentication, and there's a couple of options. You can do it through a virtual MFA, or you can do it through SMS text. But you definitely want to make sure that you're using the principles of something you have and something you know to be able to access services. And then, if you're lazy like I am, you want to manage these permissions with groups so that it's easier to tell, who has access to what, easier to revoke permissions, should somebody leave or change roles. And it gives you a much smoother interface in terms of managing these systems. Grant least privilege. That's kind of one of the basic truisms of security. Give people just enough to do what they need to do and nothing extra. Having blanket admins is probably not the best approach overall if you could avoid it. And then use IAM roles to share access. So this allows you to define the roles and then apply the users or groups to the roles, and you have a very tight view on who or what has access to what. And then put your instances in roles too. So you have the ability to assign roles to the EC2 instances, and you can group them, but in a couple of different ways. But this makes things secure because now you're fully using role-based access in IAM. And then audit. Like Seth said, it's an untrusted world, right? And we definitely want to verify. So one of the first things that you should do when you get a brand new AWS account is to turn on CloudTrail, and this will give you a log of every API call, and that includes access from the console. So the console is really built on top of API calls as well. All of this is thrown into CloudTrail, and it gives you a great opportunity to identify if there are any unexpected things happening or potentially malicious things happening, and makes it very easy to track those sorts of things. And then, if you can, don't use root. That's number 10. Actually, one of the first things I tell people, get away from using root immediately. There's a lot of danger there, and it's similar to, the operating system. With great power comes great responsibility, but also great danger. So I wanted to talk about one of the cool ways that you can control access, and you can actually do something in AWS called tag-based access. So I've got a little builder slide. It's going to show you how it works. Really we want to do, if we have some resources that we want to treat as a unit, say that we have a particular project with multiple resources, say an RDS database and some EC2 instances and some VPC rules, we want to be able to enforce these permissions even if new resources are created. That's one of the interesting things about modern applications in the cloud. Resources are very ephemeral, and you can't necessarily predict all of the resources that you'll have on the day of creation. So great example is an auto-scaling group. As new instances fire up, we want to make sure that we're enforcing those permissions. So there's a certain number of services that support tag-based access control. I went and updated this morning, so this is the very latest. But what we find very common is, storage services, compute services, and database services are the kind of the key places people are looking to do this. So how does it work? Well, we give Rob some permissions, and we say, if the tag is Project Blue, he can have rights to that. So got an instance here, Project Blue, he's good to go. Another instance here, Project Blue, he's good to go. And we can actually give him access to additional instances as they pop up when we're auto-scaling. But Project Green, he's blocked from, and it's going to actually process that tag and decide that he has no access to that, which is actually a really slick way to segregate things by project. The other thing I wanted to talk about was federated access. So say that you have more than one AWS account. You have everything isolated in a dev account, and then your production is in a completely different account. And say that Rob needs to do some work with DynamoDB. He needs to read some tables. So first of all, we're going to create a role for DynamoDB. We'll call it DDB role. And we have to allow principals from that other account the ability to assume that role. So the STS is the secure token service. Gives us a tokenized assumption of that role. And then we assign some permissions to it. So we're going to give, we're going to allow some read action to DynamoDB. And then the final step is we need to assign permissions to Rob to allow him to assume this role. And you'll see we're referencing the role in the production account, and he's ready to go. So we're going to authenticate, Rob's going to authenticate with access keys, and he's going to get back some temporary security credentials for the DDB role. And that allows him to start calling APIs. And he's actually using those temporary credentials, and those will go away because they are temporary. And this allows him to do the read work that he needs to do against the database from his dev account, but we are able to isolate that from the production account and limit it. And if we go back to one of the principles in our top 10, least privilege and segregation are very key things that we want to do in terms of security. So I hope this was interesting for you, and I'm going to hand off to Paulo, and he's going to show us how Fanatics did it.
Okay, guys, thank you, David, and hello, world. It's really a pity that you can still find people storing database credentials in version control systems or passing through emails, right? Joking apart, I'm very excited to talk about this great tool today and explain you how we are using it at Fanatics. My goal today is to present you some lessons learned and give you guys an idea of a real use case. But first, let me give you some context about our business and scale. Fanatics is the global leader in licensed sports merchandise. Our technology drives the front end, middle tier, and back office services responsible to scale millions of products. To give you a better idea of what I'm talking about, this is the e-commerce of all major professional sports leagues in the US, ranging from Major League Baseball to NHL. This is many professional teams. Some examples are Falcons, New York Giants, Chicago Bulls, Seahawks, 49ers. In Europe, we have partnership with Real Madrid or Manchester City and many more. This is actually media as well. Most major media partners, when you go to content site and you click shop, is Fanatics powering the experience. About 70% of the teams in the college football playoff are powered by Fanatics. When I'm talking about being a partner, I mean soup to nuts. We are the front end, we are the technology, operations, we are the inventory, marketing, and customer relationship. So, if you are a sports fan, you probably bought from Fanatics, whether you know it or not. Maybe going to a physical store like the NBA store that we run in New York, a few blocks from Times Square, or going to a favorite team mobile app and clicking shop, all roads lead to us. Our efforts to build a secure cloud began when we decided to re-architect our e-commerce platform. One of the biggest reasons for doing it was originated by our event-driven market. This is a heat map of Cavs versus Warriors game number 1 in 2015. This is actually a hot market for us. You can see a normal activity, but then after the end of the game, right there, the entire map lights up. What happened is our legacy platform sitting on on-premise data centers needed to be prepared for handle the peak load during a hot market. At the other times of the year, we have computational resources just sitting around. That kind of behavior is a perfect fit for the cloud, right? Now, our new platform, powered by AWS, can be dynamically scaled to fit any kind of capacity that our market needs. As a result of our cloud adoption, now we have tens of AWS accounts spread in multiple different environments, holding over 1,000 nodes and hosting more than 100 microservices. When we migrated to the cloud, our security challenges started to appear. A higher number of microservices allowed us to use any kind of programming languages or frameworks that we wanted to use, and that gave us agility. However, it also increased our exposure to risks. On top of that, we have to manage a hybrid cloud now. These are some questions that appeared during our cloud adoption. How our microservices can consume secrets, how operators can have access of those keys, how can we encrypt our user-sensitive data, such as emails, address, and so on, and coordinate keys for producers and consumers. How can we provide high availability, and how we will audit and monitor the secrets consumption. Vault answered all these questions for us, and it did that in a user-friendly and auditable way. We evaluated other options in the market, but the tools we looked at either could not cover all the use cases or were not really ready to deal with in hybrid cloud. This is a high-level view of our architecture within an AWS region. We have at least one Vault node deployed in each AZ, and we use Console as our backend storage. Vault then is working in active standby mode, so if an error occurs in any Vault node, a new leader will be elected, and our service discovery can route the request to the new health node. So here are some war stories that we had when we started to adopt Vault, and maybe it can be a good food for thought. We had an issue with Console Vault health check because a security group wasn't configured properly. So if you are using Console as your backend storage, make sure that you've opened the correct parts to the Console protocol. We actually had some issues in network performance as well. We didn't enable the enhanced network in our AMIs. That's a valuable tip. If you are using it, AWS, make sure that you have enhanced network enabled for a core component like Vault. We had problems in selecting the correct instance type to fit our needs and scale. And this is kind of related to the next war story, which is the troubleshooting. We took a good amount of time during the investigation of issues because we didn't have mature monitoring tool. And how we solved that? We built some monitoring dashboards using the telemetry data provided by Console and Vault. What you can do is configure your nodes, Vault and Console nodes, to send the telemetry metrics to a statsd server. The statsd server is responsible to aggregate all your data and send it to a Graphite database. Then you can use an awesome tool like Grafana to build nice dashboards. You can also consume CloudWatch metrics in Grafana and build a single point of view to monitor your entire cluster. This is how those Grafana dashboards look like. Okay, we have other tips for those of you that are starting to use Vault. The first tip is a quick start. So recently, AWS published a document in their page. It's worth to use it as an initial version of your implementation. Pick the right storage backend. Each backend has pros and cons, advantages and trade-offs. There are some storage backend options that doesn't support HA. Be aware of that. On the other hand, there are some other storage backends that offers a robust backup and restoration process. We use Console as mentioned before, and you can use Console snapshots to backup and restore your data. Turn on the audit backend. The audit log contains every interaction with Vault, including errors. It can be used to identify possible threats and failures. Define a break glass procedure. This is related to emergency breaks. If you see that your secrets compromised, Vault and Console offers a nice way to rotate your secrets. You can rotate your keys in Vault and use Console Watch mechanism to make your microservices pull a new secret and provide a downtime zero if you want to refresh your secrets. Another tip is to separate read and write roles and avoid list. That is to protect your system to be even more effective if there is a leak in your secrets to use Vault. When you start to use Vault, you will realize that you have a chicken or egg problem to solve. You have a way to consume your secrets, but you need to hydrate your machines with the secrets to use secrets. You can solve it using a seed Vault cluster, for example, or maybe you can use another auth backend like EC2 auth backend. So another tool is related to how we started to automate Vault. We started to automate the provisioning and the echoes and policies configuration in a single step of our automation. However, we found problems when we had to fix some role or for hardening our security. We recommend that you separate your provisioning automation from the echoes and policies configuration. That will give you the possibility to redefine your echoes and policies anytime. Another tip is to read Vault security model documentation. You will see that there are some parts that Vault doesn't cover. For example, protecting against arbitrary control of the storage backend. In our case, in Console, you should define echoes to protect your Vault key entry. If you don't do that, although an attacker won't be able to read any information that's stored in Console, it can corrupt the data. And the last tip is that you can use Console to have visibility of your search expiration date. So here's the outcome of our Vault adoption. We could offload our cryptography needs to Vault, and we leverage its state-of-the-art encryption algorithms to protect our sensitive data. We simplified our configuration management. Our internal deployment tool called Keeper can seed our microservices with the secrets that they need to access Vault, and that's it. Actually, Vault helped us to eliminate any kind of ad hoc solutions to manage secrets. In other words, helped us to avoid secret sprawl. As a result of that, we have a single system to audit and monitor. We can create now any number of named policies with fine-grained control over paths and custom TTS for your secrets. And now that through a high available system. So what are the next steps for us? We are looking towards to use Vault Enterprise. Vault Enterprise offers a nice UI, as you could see in Seth's presentation, that we can make our operators' life easier, and leverage the replication feature to achieve a better data center failover. So that's all I had. I hope you guys enjoyed, and I'm going to hand over to Amanda now. Thank you for watching it.
Thank you, Paulo. Thank you, everyone, for joining us for today's webinar. And thank you to Seth, David, and Paulo for presenting today. As we said at the beginning, this webinar was recorded, and we will make the recording available after processing. We will also send an email to everyone who registered for the webinar, the complete list of questions and answers, after we summarize all that data. Thank you so much for joining, and have a great day.